Hello, my name is Jason Breck. I'll be presenting joint work with John Seifert and Thomas Reps from the University of Wisconsin MAD-PL group and Zach Kincaid from Princeton. In this talk, I'll describe a method for obtaining numerical procedure summaries for recursive procedures. The goal is to take a program written in C and automatically analyze the program to produce summary formulas, like the one shown here, that characterize the behavior of each procedure in the program. In case of a very simple procedure, like max, the procedure summary exactly captures the behavior. For a more complicated procedure, we expect to find a summary that is a sound, but possibly over-approximate statement about the procedure's behavior. It's natural to ask why procedure summaries are useful, or how they can be used. The first way that they can be used is to answer queries about the procedure's behavior, such as whether a particular assertion in the code always holds. The second way that they can be used is as a replacement for a call to the summarized procedure. Continuing the example shown before, when we see a call to the max procedure, for which we already have a summary, we can replace the call with a new operation whose behavior is exactly described by that summary. That substitution, in turn, helps us to build a summary of the calling procedure, such as the one shown here. By proceeding in this way, we can summarize all the procedures in a program. A difficult case arises, though, when procedures contain recursive calls. We can't substitute a summary in place of a recursive call because we could only do that if we already had the summary for the procedure that we're in the middle of trying to summarize. Moreover, a situation that's been particularly challenging for some past analyzers is what is called nonlinear recursion. A procedure is said to be nonlinearly recursive if there's at least one path through the procedure body along which the procedure makes multiple recursive calls. Common examples of nonlinearly recursive procedures include tree traversals and divide and conquer algorithms. So, in this work, the high-level problem that we address is how to obtain numerical summaries for recursive procedures. But more specifically, the summaries that we wish to find are logical formulas that relate the integer variables of a procedure's pre-state and post-state, including the procedure's parameters, return value, and pre-state and post-state global variables. Note that the contents of arrays and other data structures are not in scope for this analysis. Some procedures may contain a variable that tracks the time complexity or memory complexity of a procedure. In that case, procedure summaries may be sufficient to prove a bound on the time or memory complexity of the procedure. Because the procedures may contain complicated manipulations of numeric variables, we would like to be able to find summaries that go beyond linear arithmetic, sometimes containing polynomial, exponential, and logarithmic relationships between variables. Finally, we'd like to be able to analyze procedures having arbitrary control flow, that is, arbitrary combinations of loops, branches, and recursive calls. That includes the possibility of mutual and indirect recursion between procedures. It also includes nonlinearly recursive procedures, and the specific focus of this work is on the analysis of nonlinear recursion. At several points in our analysis, we produce program analysis subproblems in which recursion does not occur. And when that happens, we assume that existing intra-procedural analysis methods can be used to solve these non-recursive subproblems. The new analysis method that I'll describe can be seen as a combination of two past approaches for finding numerical invariants. First, template-based invariant generation, and second, recurrence-based invariant generation. We call the combined technique height-based recurrence analysis. As a next step, I'm going to describe what these two past approaches are at a high level, and then I'll explain how we put them together. Template-based techniques first specify the form of the invariant using a template containing numerical unknowns. Then they find constraints on the unknowns, and they solve those constraints to obtain the invariant. One disadvantage of template-based techniques is that they need to specify a priori the set of terms that can appear in the invariant. In particular, if you're interested in nonlinear mathematical relationships, you'll typically need to specify in advance the maximum degrees of polynomials or bases for exponentials that can occur in your invariants. Recurrence-based techniques avoid that problem. They provide a way to establish mathematical relationships between variables that include polynomials, exponentials, and logs, essentially because those kinds of complicated relationships can arise naturally as the solutions to simple recurrence relations. Recurrence-based techniques are well suited to characterize the linear sequence of program states that occur during the execution of a loop. First, the technique analyzes the body of the loop to find recurrences. The recurrences relate the values of variables after k iterations of the loop to the values of those variables after k plus 1 iterations. Then, a closed-form solution to that recurrence can tell you about the program state after any number of iterations. However, we're interested in the analysis of nonlinearly recursive procedures. Executing that kind of procedure leads to a tree of recursive calls rather than a linear sequence of states, and so it's not obvious how to characterize the resulting set of program states using recurrences. To analyze such procedures, we developed a new variant of template-based analysis, in which the unknowns in the template are functions rather than numbers, and the constraints on those unknown functions are recurrences. To see how height-based recurrence analysis works, consider again the execution of a nonlinearly recursive function and the resulting tree of recursive calls. The idea is to divide up the vertices of that tree, which represent different calls, by the height of the vertices. Height 1 represents the base case of recursion, which are the leaves of this tree. A call at any height h may make further calls at heights strictly less than h. The unknowns in the template that I mentioned before will be constrained using recurrences that are indexed by height. And in this respect, our procedure summarization technique is related to some past work in automated complexity analysis. Now I will walk through the steps of height-based recurrence analysis on an example procedure. On the left side of your screen, you see some code from a recursive procedure that we would like to analyze. This procedure searches for an answer to the subset sum problem, a classical NP-complete problem, so the procedure will have exponential time complexity. For the purposes of height-based recurrence analysis, I'll consider a simplified version of the procedure body in which all but the most relevant parts have been removed, as shown here. Likewise, although our full analysis would consider several features of the procedure, my presentation will focus on just two features. I will show how to obtain an upper bound on the return value and an upper bound on the value of a global variable in this program that is named n_ticks. The variable n_ticks is incremented on the first line of the procedure and not modified anywhere else. Because of what we know about the complexity of this procedure, we expect to find an exponential bound on n_ticks. Observe that a path through this procedure may perform either 0, 1, or 2 recursive calls, so the procedure is nonlinearly recursive. The first goal of height-based recurrence analysis is to derive the procedure summary template. The first step towards that goal is to analyze the base case of the procedure. The base case, by definition, is free of recursive calls. Therefore, we can use existing intra-procedural analysis methods to produce a summary of the base case, like the one shown here. Moreover, we can produce a summary in a particular form, namely, a conjunction of inequations over prestate and poststate variables with a constant on the right-hand side. In this case, a primed variable occurrence, such as n_ticks prime, represents the value of that variable in the poststate, and an unprimed occurrence, such as n_ticks, indicates the value of that variable in the prestate. So, this summary says that in the base case, the return value is at most 0, and the variable n_ticks increases by at most 1. Now, we produce the procedure summary template by generalizing the base case summary. To do that, we replace each constant right-hand side with a function symbol, representing an unknown function, as shown here. As a result, we have a template summary that we know is applicable to the base case at least because if we substituted a 0 in place of b1 of h and a 1 in place of b2 of h, we would get back our original base case summary. For that reason, the procedure's base case corresponds to the initial condition of our height-based recurrence. Eventually, though, we want to replace each of the unknown function symbols with the closed-form solution of some recurrence. Now that we have a procedure summary template, our next goal is to find recurrences that constrain the unknown functions in the template. To do that, we analyze a modified, non-recursive form of the procedure in which the recursive calls have been replaced by a new operation whose effects are exactly described by our template. That is, this new useTheTemplate operation returns a value that is at most b1 of h, and it modifies the variable n_ticks, increasing it by no more than b2 of h. Now we ask the following question. What is the tightest single bound on the return value that holds on every path through the modified procedure body? Because we've replaced the recursive calls, we can now use existing intra-procedural analysis methods to answer this question. That analysis yields a bound on the return value in terms of the unknown b1 of h. If we exit at the first return statement, the return value is bounded by b1 of h plus 1. If we exit at the second return, the return value is bounded by b1 of h. Thus, the tightest single bound that holds on every path is b1 of h plus 1. We take the right-hand side of that bound to be the right-hand side of a recurrence, saying that as height goes up by 1 in the tree of recursive calls, the maximum possible return value goes up by 1. For the variable n ticks, we can perform a similar analysis. We ask, how much can n ticks increase between the entry and exit of the modified procedure? Again, we can use existing intra-procedural analysis to answer this question, and that analysis effectively reasons as follows. N ticks increases by exactly 1 at the first line. Then, when we reach the first use the template operation, we know that n ticks will increase further by at most b2 of h. If we then go through another use the template operation, n ticks will increase again by at most b2 of h. So, what is our bound on the increase to n ticks? Well, the tightest single bound that holds on every path is 2 times b2 of h plus 1. As before, we take the right-hand side of that bound to be the right-hand side of a recurrence, saying that as height goes up by 1 in the tree of recursive calls, the maximum possible increase to n ticks doubles and increases by 1. Now that we have recurrences, we just have to do a few more steps to produce the final procedure summary. First, we give the recurrences and the initial condition to a recurrence solver to obtain a closed-form solution. For that purpose, we can reuse a recurrence solver that was used in past recurrence-based invariant generation techniques. We then substitute the solution back into the template to produce a height relative summary, which relates the procedure's pre-state and post-state to the height of the tree of recursive calls. We have a further analysis, which I'll describe next, that obtains a bound on the maximum possible height of the tree of recursive calls in terms of the procedure's parameters. I won't go into much detail about this height-bound analysis. It's another recurrence-based analysis, and it attempts to find an upper bound on the number of recursive calls that we can go through before reaching a base case. In other words, it tries to find a bound on the length of the longest root-to-leaf path in a tree of recursive calls as a function of the procedure's parameters. For more information about how the height-bound analysis works, have a look at the paper. In the case of the running example, though, the height-bound analysis produces a height bound like the one shown here. Note that the variables n and I that occur in this bound are two of the procedure's parameters. With that bound in hand, we're finally ready to construct the procedure summary. The final step is to conjoin the height relative summary and the recursion height bound to obtain the procedure summary. In this example program, the procedure summary yields a bound on the return value that is linear in the procedure's parameters and a bound on the increase to n ticks that is exponential in the parameters. And with that, we've finished the application of height-based recurrence analysis to this example program. We implemented height-based recurrence analysis in a tool called CORA, which stands for Compositional Higher Order Recurrence Analyzer. To evaluate the analysis, we applied CORA to two kinds of recursive benchmarks from the literature, namely complexity analysis and assertion checking benchmarks. First, we applied CORA to a set of 12 complexity analysis benchmarks, all of which are nonlinearly recursive. In this table, we show the actual complexity of each benchmark, along with the asymptotic complexity of the bounds produced by CORA and of a collection of other analysis tools. The rightmost column, marked Other, shows a combination of results produced by several other analysis tools that are specialized for the task of complexity analysis rather than general procedure summarization. Note that no single tool produced all the results in that column. ICRA is an earlier invariant generation tool built by the same authors as CORA during earlier work on recurrence-based analysis. ICRA uses the same analysis framework as CORA, and it uses recurrence solving when analyzing loops and linearly recursive procedures. However, it reverts to Kleene iteration rather than recurrence solving when analyzing non-linearly recursive procedures. Comparing the CORA and ICRA columns shows the benefits of applying recurrence solving to non-linearly recursive procedures. In two cases, the bound produced by CORA is asymptotically tighter than the other tools. Overall, the results show that CORA's technique is able to prove that complex mathematical relationships hold in recursive procedures. We also applied CORA to a set of standard assertion checking tasks from the literature. Within the software verification competition suite, we chose all the benchmarks containing true assertions in the recursive subdirectory of the Reach Safety Recursive category. Cora was able to prove the assertions in 8 out of 17 of the benchmarks. There were 3 tools from the SVComp competition that were able to prove the assertions in a larger number of benchmarks than Cora. Ultimate Automizer could prove 12 of 17, UTaipan could prove 10 of 17, and VIAP could also prove 10 of 17. However, those 3 tools were roughly an order of magnitude slower than Cora, and all the tools from the competition other than those 3 were able to prove the assertions in fewer benchmarks than Cora. From these experiments, we conclude that Cora's procedure summaries are sufficiently precise to be useful in proving assertions in a standard benchmark suite. In conclusion, I've described a new method for finding procedure summaries that combines elements of past template-based and recurrence-based methods. The method is able to find procedure summaries that include polynomial, exponential, and logarithmic relationships. It can analyze procedures having arbitrary combinations of loops, branches, and recursive calls, including nonlinear recursion. And the procedure summaries computed by the method are sufficiently precise to prove assertions and find complexity bounds. Thanks very much for your attention.